I started. Is that good?
Did you start?
Yeah.
Jennifer.
Hello.
Is it? Big thing is that we hit that.
Hey Justin, if you hear this is not for you.
Come on, Abby.
All right, gang.
I have today a pretty full hour, so if I can have your attention, we're going to be going the rest of the way in this chapter, and we have a lab on Monday, hopefully on Monday, and we need to be ready for it, and that's going to include some of the things that we're talking about today. The lab on Monday it's a full lab. There's no write-up for it. We're just going to do it all in 1 hour and have it done by the end of the hour and turn it in. But it's going to keep you busy for sure. Great experiment too. I think you'll enjoy it. Let's take a look. Now, yesterday we were into this slide. Do we not do any of this slide, or do we do part? None of it. Nuts. Okay, well I'm going to cover part of this up. Let's take a look. The rate of a reaction is dependent on how frequently the particles are colliding with each other. We've got to have particles running into each other. There's really two things, these two things, about the kinetics of a reaction that we have to know. If you're still writing, I'll come back to this slide. Just want to show you the next one. When we're looking at number one, colliding particles must be oriented properly. When you have a bigger molecule, sometimes the molecule will have parts of it that are not reacting. And so I want to just show you a visual of what that proper orientation is about. If we have these two parts, if our compound that we're trying to make is that, you have these two things running into each other. These will probably make one of those because they're oriented correctly. However, if this one is moving this way and this one's moving that way, they're going to hit each other. And since they don't really fit together like this way that they're hitting, those are not, they're going to collide, but they'll just bounce off of one another and go on their way and not react. Same thing for these two. If these two run into each other, they're just going to bounce off because they're not oriented properly. They need to be oriented kind of like this, where they come together and the right side of one molecule is hitting the right side of another in order for them to make a change. It's got a fancy name. It's called the steric factor. There is a way to calculate the steric factor. Ready?
Is it like margin of error, or does it have to be like exact?
Yeah, there is some margin of error, for sure. And part of it is how much energy they run into each other with. If they're not moving fast, they're going to bounce off anyway. If they're moving really fast, they'll probably have enough energy. Remember, this is just a model of it. Keep in mind that we have to have enough energy to break the reactant bonds apart as well as the orientation of them. So there's two things really kind of at play with collisions causing reactions. Now the activation energy is a big deal. The reacting particles need to have enough energy in that collision to cause them to break apart. Bonds have to break in order for things to be rearranged. If I can go 2 slides ahead, we see this. Now I started the chapter with this picture. We have the reactants with a certain amount of energy, the products with a certain amount of energy. I told you at the beginning of the chapter, the beginning and the end, that has to do with thermodynamics. Is energy overall given off or taken in? What happens in the middle? That's the kinetics. The reactants, when they run into each other, have to have enough energy to be able to break. Going up the hill is the breaking of bonds. So if the reactants are real stable, it's going to take a lot of energy to break them, and you're going to have a real high activation energy. If they're unstable, then it's not going to take much energy. They're easy to break apart. So the size of this hill also kind of dictates how fast the reaction is going to go. We call that amount of energy to get from the reactants in order to have them broken apart and ready to rearrange. We call that the activation energy. And that's symbolized like this, the capital E for energy with lowercase a, activation energy. All right? So here's where bonds are breaking. Energy's got to be put in to get energy to bonds to break. And then over here, bonds are forming. It's giving off energy. That bond breaking, bond forming idea with regard to energy is key. All right, so back here is what I'm talking about. Where does the energy come from? Well, the particles are moving, and as they move, they have a certain kinetic energy that can be used. So if they have enough kinetic energy when they run into each other, that could be what it needs to break the reacting things apart. Kind of like a dish. If you have a dish that's a centimeter above the floor, you drop it, it's probably not going to break. There's not enough energy for it. But if you hold a dish high up and let it go, boom, and it's going to hit with more energy and break apart. Same kind of thing for this. All right, so what does temperature have to do with collision theory? Well, it kind of goes back up to this. If you increase the temperature of a reaction, the particles have more speed. They're moving faster, and they collide more frequently. And so the more frequent collisions typically means a faster reaction. And since they're moving faster, they're going to have more kinetic energy. Therefore, more collisions are going to have the activation energy.
It's an exothermic.
A lot of times with an exothermic reaction, as the reaction occurs and heat is given off, heat's being passed out to other reacting particles. And so most reactions that are exothermic, as they go on, they go faster and faster. Like a fire, for instance. When you start a fire, it's hot, it would burn you, but it's not really very hot. As it continues to burn and the wood starts to heat up more, the particles are moving faster, more heat is given out because the burning goes faster. So exothermic reactions normally start slow and they get faster as they go on because more energy is given off, the particles are moving faster, the more the reaction goes.
So it's the opposite for endo.
Yeah, it would be the opposite. Yep. Endo probably starts fastest, and then as it goes on, it gets slower and slower. Okay, we good with this one? So now we've seen these two. There's an equation. It's a nice, pretty equation, isn't it? We have talked about finding K. When you have a differential rate law, you plug the values once you find the orders in, and you calculate the K value. Well, there's another way to find K. This was developed by a guy named Svante Arrhenius, the same guy that came up with Arrhenius acids and bases. These are all the factors that go into the K value. And I've talked several times this chapter about how it's the K value that really indicates what the speed of the reaction is. The higher the K, the faster the reaction. All these things affect the K. Now this E right here is the number E, E to a power, right? But the Z, P, EA, and R and T, of course, should be defined. what do we know up here? We know what activation energy is now. We know R, it's a thermodynamic constant. And we know T is temperature. What's going on here with the Z and P? Both Z and P have to do with how fast the particles are moving and the steric factor, how they're oriented. So how would these terms affect the rate? The more frequently collisions happen, the faster it goes. So K is directly related to the frequency of collisions. Also directly related to the fraction of collisions that have the right orientation. If you have small particles that are reacting, the P term is going to be high. If you have big complex molecules happening, reacting, the P value is going to be smaller. Because you're going to have more collisions that don't hit the right spot of the molecules, and they bounce off of each other and don't react. Now, the rest of them, EA is the activation energy. Now, it does say about the activation energy, it's inversely related to K. Could you mathematically justify that if EA is high, the K is low? I think you could. Activation energy is always a positive number. How much energy do the reacting things need? So if activation energy is a negative exponent on E, can you make sense of that in your brain?
Yeah.
Then it's inversely related to K. The higher the EA, the smaller the K value. Because really, this is 1 over E to the EA power, so the bigger the E, the bigger the denominator is. Okay, then R is 8.31 and T is the temperature. Make sure you use Kelvin. Normally the problem is going to give you the temperature in Celsius. You have to change it to Kelvin. So you see there's several things that affect the rate of a reaction. They're all accounted for in here. These two first terms out here in front of the E, the Z and P. When Arrhenius came up with this model, he recognized that these two could be combined together, and they're normally, for a reaction, pretty constant. It has to do with, well, the temperature. The temperature is going to affect the Z term. But at the same temperature, they're pretty constant because the size of the molecule is what the size of the molecules are reacting, and they don't really change. So he said, and he named it A stands for Arrhenius, is equal to that ZP term. We call that the frequency factor. So this equation is normally expressed with an A out in front of the E term rather than ZP. So this is the way to that you'll expect to see this relationship between K and the other things that affect it. Sir?
Will Z be given to us? Can we just plug in
Yeah, sometimes A will be given to, or maybe you'll have a problem in which you'll have two A's and they cancel out or something like that. Normally we don't do anything numerically with A. It has to be there in the equation, but we'll find a way to not use it. So the activation energy of a reaction really affects how fast it goes. there's something that we can do to lower the activation energy.